Okay, so let's continue our discussion. Let me go full screen and turn on the laser. Okay, so we were just saying that by staging the hardware into different stages, then we can have a situation where while one instruction is writing back into its registers, then another instruction can be reading from the memory or accessing the memory at the same time. Another one can be using the ALU. Another one can be reading from the registers, and another one can be fetched from the instruction memory and updating the PC. So the reason that we can do these operations at the same time is because we have these resources that can be used at different stages for different operations. So let's see conceptually how this thing works. So the idea is that you are going to fetch an instruction during the first step, and then as that instruction moves on to the second stage and you're beginning to get the operands or the registers for the second instruction, then you are going to read the next instruction. So you're going to fetch the next instruction. So now you have these two operations happening at the same time. So in terms of hardware, basically that means that second instruction is reading the registers, and the first instruction is reading the registers, and the second instruction is being fetched from the memory at the same time. So these two are happening in parallel, okay? And then similarly, at the next stage, instruction 1 will be executing, instruction 2 will be getting its operands from the registers, and then instruction 3 will be fetched. So again, going back to our hardware, instruction 1 will be here at this stage, instruction 2 will be here at this stage, and instruction 3 will be read from the memory. And all of these are at the same time. Okay, that's the key. So continuing the operations, then instruction 1 will access memory, instruction 2 will execute at the same time, instruction 3 will get its operands, and instruction 4 will be fetched. And then moving on to the next stage, then instruction 1 will finally finish, write back. Instruction 2 will access memory, instruction 3 will execute, instruction 4 will get its operands. So at this point, the pipeline gets full, and then we'll begin producing the result one stage at a time. So at this stage, instruction 1 completes, and then at the next stage or the next step, instruction 2 will complete. And if I continued my operations beyond this point, then instruction 3 will complete in step 7. So once we reach the saturation point, similar to the pipeline that I showed you before, we'll start getting results one step at a time. So now let's go back to the design that we had and start looking at some of the details and some of the possible problems that may come up. Now notice these blue lines here, which I'm highlighting in yellow, this one here and this one here. These are problematic because what's happening is that we are writing into a register, in this case, at a stage later than when so in other words, we have read the values from the registers, but we are writing into them in some stage down the road in the future. So we want to go back and update our register counters while at the same time some other register is or some other instruction is reading the registers. Then the same thing happens with the program counter. We have a situation where at a later stage in the pipeline, we are trying to write back into the program counter as program counter is being read for some of the instructions down the road. So how do we handle this? Well, basically what this means is that we are trying to read and write into the same registers or the same file at the same time during the same clock cycle. And the solution, if you remember, that we came up with was basically writing during the first half of the clock cycle and reading during the second half of the clock cycle. So to remind you again, the flip-flops are stable during a clock cycle. So a clock cycle is when the clock goes from low to high, and then during the halfway point it goes from high to low and stays low, and then finally at the end of the cycle it goes back high again, and then after that point it will keep repeating. So as clock cycle is low and it comes in, so this signal is 0. That 0 means that this Q is stable, it won't change. And that 0, and then that 0 translates this into a 1, which means that this can change, but that change won't have an impact on the outcome because this is 0, and it will latch 2 won't change. So at the time that we go from 0 to 1, then this clock signal changes. This becomes 1, and when it becomes 1, then it will read whatever the value of D is that came through the first latch, and that becomes the new Q. And then as this 1 is inverted and becomes 0, will latch or lock up latch 1, and therefore latch 1 won't change anymore. So at that point, whatever the value of D was will remain unchanged here, and if this remains unchanged, that means that the output of the Q will remain unchanged. Okay, so during the clock cycle, no matter whether it's high or low, the output Q will not change, or flip-flop won't change. And it only changes at the beginning of the next clock cycle when it goes high. Then at that point, the input will be written into the second latch and will cause Q to change. So the only time, basically the only time that we can update or write into a register or a flip-flop is at the beginning of the clock cycle. So the net effect is that if you take this clock cycle in the middle, whatever changes you made to the registers D and Q in this previous cycle will take effect at the beginning of the next clock cycle during this half cycle, causes a change in Q, and then it won't change during the second part. So during the second part, we can read the flip-flops. During the first part, we can write into the flip-flops. And then as the second cycle completes, then it's going to begin to write into the registers again, which will take effect during the following cycle. So that writing into the registers will take effect during the following cycle. So in this operation, then we write into a register in the first half cycle, and the value that we write is the result from the previous cycle, and then we read whatever we updated in the second half cycle. So the rules are, and that also applies to our pipelining, we write a register or program counter in the first half of the clock cycle, and then we read the register or program counter in the second half cycle. Okay, so that's how we are able to read and write into registers in the same clock cycle. So let's take a look at the effect of this on pipelining and see how it works. So let's assume that I have a pipeline in which I have instruction 1 fetched, and then I go to the next cycle, I decode the first instruction and read the operands for it, and then in the next cycle I execute it, and so on. So I'm not showing the rest of it, I'm leaving blank because it's not relevant to what we're talking about. Now, I'm also showing this kind of a light dashed line here in the middle to show the half cycles. So for the first cycle, which begins here and ends here, the half cycle is in the midway point right here. And for the second cycle, the half point is here, and so on. Okay? Now, after the first instruction has gone through the pipeline, then in the second cycle, I fetch the next instruction, and I go through and do the same things. And then in the third cycle, I get the third instruction. So let's see how program counter is updated. So let's focus on the middle part, on this part here. Now, in order to fetch this instruction, what happens is at the end of the previous clock cycle, meaning at this point here, previous instruction updated the program counter somehow. Either it added 4 to it or computed a destination address and put that in program counter. But remember that that update of that program counter won't take effect until beginning of the next clock cycle. So we always write at the beginning of the next clock cycle. So that updating of the program counter, which was supposed to take place at the end of this cycle, cycle 1, actually takes place during the first half cycle of cycle 2. So as I1 transitions to I2, then that's when the PC is updated. So if PC is updated during the first half of the second cycle, then we can read the PC in order to fetch instruction 2. Then we can fetch it at the location specified by updated PC at the beginning of the second half cycle of cycle 2. So net effect is that during the first half cycle, PC was updated, was written into. In the second half cycle, PC is read. Now, during the second half cycle, PC is read and it's updated also, PC plus 4 and so on and so forth. But that update won't take place until the next half cycle as you transition, as your clock transitions from 0 to 1 in the next half cycle. So it is at that point that the PC is updated again, and then we'll get the, basically during this time, and then we'll get the third instruction during the second half cycle of cycle 3. Okay, so that's how program counter is read from and updated in the same cycle. We always write into the program counter during the first half cycle, and we read from it during the second half cycle. Okay, so with this, I'm going to stop this portion of the Monday video, and then I'm going to continue the rest of the Monday lecture in the next video.